I hope you guys have all been enjoying the presentation so far. Thank you all for being here today. I'm excited to share what I've been working on. So my project is looking at the responses of harmful algal bloom causing phytoplankton species and taxa to atmospheric rivers along the coast of California. Here is a quick outline of what we're going to be talking about today. I'm going to get started with a background on harmful algal blooms as well as atmospheric rivers. That will lead me into my research questions, followed by the methods that I use to answer those research questions, into my results, and of course I'll close this out with some discussion and conclusions. So harmful algal blooms can occur when specific species of phytoplankton are in the water column, and they can cause a perturbation to the ecosystem, typically via two different mechanisms. The first mechanism is that they can release toxic substances into the water column, and when these are ingested by mammals, including humans, fish, and birds, this can cause illness or in some cases even death. The other mechanism is that when these phytoplankton get to a great enough abundance, the decay of their bloom can deplete the oxygen out of the water column, making it hypoxic. And both of these mechanisms can have really big implications in terms of human health, ecosystem health, and economics. Because it can impact fisheries really heavily, recreational industries, as well as tourism. And finally, one thing that's really important to note is that harmful algal blooms have been globally on the rise in the face of climate change, and so this is a really important thing for us to be discussing today. So putting this into the context of California, California has a Mediterranean climate, meaning that we have wet winters and typically long, dry summers. And this means that we have long dry spells during which pollutants are able to build up on land, and then these are punctuated by rainstorms that are able to carry these pollutants into the coastal waterways. Also, to consider this through the lens of climate change is global climate models predict that this polarization will be amplified, that we will have longer drought conditions followed by more extreme precipitation conditions. So as I mentioned, much of California's precipitation comes through atmospheric rivers, or ARs. These are temporary rivers of water vapor in the atmosphere that's transporting massive amounts of vapor, typically from the tropics into the mid-latitudes, and they are strongly correlated with orographic precipitation when they make landfall. And atmospheric rivers can account for about 30 to 50% of the water in California. And then one variable that is going to be super important for you all to remember throughout this presentation is going to be the vertically integrated vapor transport, or IVT. And this is essentially a measure of how much water is being transported through the atmospheric column, and I am going to be using this variable in a lot of my analyses. And this is also how we determine both the occurrence as well as the magnitude of an atmospheric river through the IVT. So I really wanted to understand the relationship between this meteorological phenomenon of atmospheric rivers and harmful algal blooms. So my research looked at two specific research questions. My first question asked if the abundance of specific harmful algal bloom causing phytoplankton taxa is correlated with the magnitude of the IVT in a region. And my second question asked if the abundance of specific harmful algal bloom phytoplankton taxa is impacted when an atmospheric river comes through a region. So that leads me into my data and methods. For this study, I used two different data sets, one that contained phytoplankton abundances and one that contained IVT magnitude as well as a chronology of atmospheric rivers. The phytoplankton data set was collected by the Harmful Algal Bloom Monitoring and Alert Program, and this was collected weekly and contained 2 diatom species, 8 dinoflagellate genera, and 3 other groups. So there were 13 counts collected weekly in total. And most of these locations were collected from 2008 through present. And then my locations are going to be here on this map. These are all of the locations that are part of HabMap, but I didn't use Trinidad Pier because they didn't have any available phytoplankton data, so everything was Bodega Pier down to Scripps Pier. And then my IVT data was collected by the European Center for Medium Range Weather Forecasts, and I got it from the Center for Western Weather and Water Extremes. And this was collected daily, and they collected it at every 0.25 by 0.25 degrees latitude grid cells along the entire west coast of the United States. And this data set contained the IVT daily average, so an accurate representation of how much IVT that day, an IVT daily maximum, so the greatest value that was recorded for that day, and a categorization as to whether or not the IVT was a great enough amount to be considered an atmospheric river for that day. And this was a longer data set, so I chopped it down to be equal to 2008 to present to match my phytoplankton data. And also to make my weekly phytoplankton data match my daily atmospheric data, I averaged my atmospheric variables over the 7-day period prior to each phytoplankton count in order to get a representation of the week for that. So that moves me into my data analysis techniques. I primarily use 2 different techniques to answer my 2 different research questions. The first technique, I calculated the correlation coefficient, also known as the R value, with the IVT daily average and the IVT maximum average, or IVT maximum value. And for both of these correlations, I did this with a 95% confidence interval, meaning that I only accepted values that had a p-value of 0.05 or less. I also did this through 3 different analyses. I used the raw data to do a linear regression. I took the log base 10 of my phytoplankton abundances as a semi-log, and I took the log base 10 of both of my variables for a log-log. And then, in order to answer my question about if atmospheric river occurrence impacted the abundance of harmful algal bloom forming phytoplankton taxa, I separated all of my phytoplankton counts based off of whether or not an atmospheric river came through that week. And then I performed a 2-sided Wilcox and rank sum test, which told me whether or not these 2 distributions were considered statistically equivalent with equal medians or not. So that brings me into my results. So I really wanted to understand my results in the context of the IVT and atmospheric river occurrence at each of my sampling locations. So this is showing all of my sampling locations with the atmospheric river frequency on the left and the IVT median value on the right. And the large red bubbles are going to be indicating a higher atmospheric river frequency and a higher IVT magnitude, and the small blue bubbles are indicating fewer atmospheric rivers and a smaller IVT magnitude. And also, for the purpose of my study, I considered everything at Monterey Wharf and northward as Northern California, and everything at Cal Poly Pier and southward as Southern California. And so these results found that Northern California experiences atmospheric rivers 2.6 times more often than Southern California. And Northern California also has an IVT on average of 1.4 times greater than Southern California. So now, as I mentioned earlier, I found the correlation coefficient between the harmful algal bloom forming phytoplankton taxa abundance with both the IVT daily averages, which the results are shown here on the left, and the IVT daily maxima. Also, as I mentioned earlier, I did this as 3 different analyses. All of these analyses yielded very similar patterns, and the semi-log had the most significant correlation, so I'm showing that one for simplicity. So what you're looking at here, you see all of my phytoplankton sampling stations along the coast of California, and then along the x-axis, I have all of my phytoplankton taxa. And also note that they are all collected on the coast. They're only spread out horizontally for ease of viewing taxon-specific patterns. So all of the small black dots are going to be locations that did not yield a significant correlation. The bubbles are places that did, and the red bubbles are indicating a positive correlation, meaning that as IVT increases, phytoplankton increase. And the blue bubbles are indicating a negative correlation. So as IVT increases, phytoplankton decrease. So now that we know a little bit of what we're looking at, let's look at some of the trends here. So the first trend that I want to point out is going to be this positive signal up in Northern California. And this trend really came out very clearly in the linear analysis, but you can see it here in the semi-log as well. And my next trend is going to be the negative correlation that came very strongly in much of Southern California. I also want to note the different taxa that yielded each of these significant correlations. For a lot of them, they were different taxa that yielded the positive correlations than the ones that yielded the negative correlations, except for serratia, which will be important later. I also noticed that there were a lot more significant occurrences with my analyses with the dinoflagellate taxa than the diatom taxa, but I also had a lot more dinoflagellates in this study. And finally, there were a lot more significant correlations when I did my correlations with the IVT daily maxima than with my IVT daily average. So now I want to move into the results of my second analysis, where I separated all of my phytoplankton values based off of whether or not an atmospheric river came through the region that day, and then did the Wilcox and 2-sided test to understand if these were considered statistically equivalent distributions. So again, we have all of my phytoplankton sampling stations along the coast of California and all of my taxa on the x-axis. The small black dots are going to be locations that yielded an H value of 0, meaning that they were considered equivalent distributions when an atmospheric river was present versus when it was not. And the bubbles are going to be locations that they yielded an H value of 1, meaning that they did have a statistically different distribution. The blue dots are going to be all locations that had a smaller median after an atmospheric river, and the one red dot, which is Symposium, had a larger median after an atmospheric river came through the region. And so I was really expecting a lot more positive relationships here than I saw, and you can see clearly that there are essentially all negative correlations except for the one instance of Symposium at Newport Beach. So that brings me into my discussions and conclusions. So I just kind of want to recap some of the trends that we saw here. The correlations were significant. I wasn't sure if I was going to get any significant correlations, but I was very excited to see that I did. And these correlations varied by taxon as well as by latitude. When we were looking at the IVT analyses, we saw that Northern California had, in general, positive correlations, and Southern California had a lot of negative correlations. And this can possibly be explained by the latitudinal trend that I showed with the first graph of IVT and atmospheric river frequency. A lot of the locations that were more likely to have an atmospheric river come through near San Francisco at Bodega Bay and Tomales Bay, they were more likely to have a positive correlation. And this could be because when an atmospheric river comes down through San Diego, it's more of a disturbance to the ecosystem, and so that could be one reason for the negative correlations that we saw. And so for my analysis where I looked at the occurrence of atmospheric rivers and how it impacted the abundance, all of my latitudes essentially had a negative correlation with atmospheric rivers. And this means that the mechanism is rather unknown. I was going into this project thinking that my idea of pollutants building up on land during a dry spell and being washed into the waterways after an atmospheric river would put influx of limiting nutrients for phytoplankton into the water column, which would cause a harmful algal bloom. And that would be represented by positive correlations in this analysis. But clearly there were a lot of negative correlations, so there's various mechanisms that I did not address in this study that should be addressed in further studies. So here are some alternative mechanisms that I think could be largely responsible for some of the trends that we saw here, and some various variables that I would love to take into account in further studies include biological variables such as nutrient availability and taxon-specific seasonality and lag, and several physical variables such as the seasonal cycle of IVT and atmospheric rivers, precipitation data, temperature, light, salinity, and there's also a lot of wind and sea current impacts that are associated with atmospheric rivers that need to be taken into account, and of course the geography of California as well. So finally, this brings me to my concluding remarks. There is a statistically significant relationship between these variables, and this conclusion does bear a heavy weight because these variables have not been correlated before, so these conclusions are broadening our understanding of how atmospheric rivers can interact with the ecosystem. We also saw that IVT magnitude as well as atmospheric river occurrence can be a predictive variable for harmful algal blooms, and this means that forecasts including IVT data can be implemented to increase the effectiveness and accuracy of harmful algal bloom warning systems, and this could possibly avoid some health issues and economic loss. Looking at this through the lens of climate change again, in a world with more atmospheric rivers, based off of my conclusions, this could mean fewer harmful algal blooms. However, as I mentioned, this is a pretty simplified view of a very complex air-sea interaction and complex physical and biological interaction. So that we need to understand more in order to really see how that will impact harmful algal blooms in the future. But one small conclusion from this is that as IVT increases, not to the full extent of an atmospheric river, specifically in Northern California, this is likely to increase harmful algal blooms in Northern California, which could have some negative impacts. And finally, further research needs to be done in order to understand the full mechanisms going on here. I really hope that this study was able to open the door to understanding this complex relationship and add to the scientific conversation surrounding why harmful algal blooms have been on the rise. And with that being said, I would like to thank my amazing Capstone committee, Dr. Jason Cordiera, Dr. Matthew Masloff, and specifically to my chair, Professor Peter Franks, who invested in me weekly on this project. And thank you to Corey and Mark, Hannah, my wonderful cohort, the Frank's Lab group, the CW3E, and to my amazing family. So thank you, guys. Any questions? Yeah, Yash.
First, I'd just like to say you had some really complicated data and you explained it in such a clear and approachable way, which is really impressive.
Thank you.
When these algal blooms happen, are there certain species that are more, are there certain like usual suspects on which species are going to cause the bloom, or is it pretty random of the species that you showed us?
Yeah, so all of the species that were collected by HabMap, that organization that I got my data from, or the program that I got my data from, all those species or taxa are going to be phytoplankton that cause harmful algal blooms, and they only count the ones that are known for causing harmful algal blooms. However, there is variation within that list. I did have a slide, but for time purposes, I got rid of it, and it's all in my paper. The different harmful health impacts that each species can have. The diatoms are known for causing domoic acid to be released into the water column, which can have a lot of really bad neurological impacts on humans. And so that's kind of the main culprit of harmful algal blooms, but all of these cause red tides, and various dinoflagellate genera also release different neurotoxins and toxic substances. So, yeah.
One more? Oh.
Hi, really great talk.
Thanks.
I'm wondering, so you mentioned possible mechanisms for the relationship between atmospheric rivers and harmful algal blooms. So I'm wondering what approaches can you think of to try and like establish the pathways for those mechanisms?
Definitely. I have a lot of ideas of the different approaches that I've been thinking of. I would really love to nail down the lag more specifically, because I did a 7-day average for all of the different taxa, but it would be cool to nail down the lag for the specific taxon. I also would really love to include precipitation data. Since all of my correlations were with IVT, and IVT doesn't always mean runoff, it would be very interesting to look at specifically the precipitation and how that has a role. But there's so many different variables. Cloud coverage I would love to look at, although that might not be taken into account with the 7-day lag. But osmotic stress and different salinity impacts could also have a really big role, because there was a study that came out this year from someone in our class looking at the freshwater plume that comes from atmospheric rivers, and there is a really strong signal from that, and so it would be interesting to look at the salinity as well, and just doing similar analyses where I take into account nutrient data, precipitation, salinity, light availability. Yeah, thanks for the question.
One more question?
Any other questions?
Did someone raise their hand? Oh.
Hey, Jeri, great job.
Thank you.
And two things. One is there is actually red tide going on right now, or a harmful algal bloom going on.
Yes, I saw your email.
Yeah, okay. I wasn't sure you'd seen that. Yeah, I just found out about it this afternoon.
Very exciting.
All up and down the coast. The second thing was, what a great study. I'm not sure you emphasized it. You said it, but it went by quickly. Nobody's ever looked at this stuff before, looking at the effects of atmospheric rivers on harmful algal blooms. So I'm just blown away at how much you did in such a short time, and the fact that you found any significant correlations is a really big deal. And so I'm hoping we can pursue this. And it was a delight having you in my lab and in my group, and thank you so much. Looking forward to finishing this off and seeing if we can publish it. Great job.
That'd be awesome. Thank you so much.